Physical GCMs, however, were limited in their abilities to account for the intricacies of atmospheric convection or oceanic currents, and soon climatologists turned to mathematical GCMs. Contemporary mathematical models depict Earth's climate in its entirety, and the acronym GCM now also stands for Global Climate Model. Solving the mathematical equations in GCM seems to tax whatever computational resources are available. Lewis Fry Richardson, while serving as an ambulance driver during World War I, would work on differential equations in his head as a diversion from the horrors of the Western Front. In one such effort, he developed a primitive atmosphere model and, using just paper and pencil, took 6 weeks to calculate air movements across Western Europe over an 8-hour period. Digital computers, which were developed near the end of World War II, were well suited to the repetitive nature of such calculations. The first large-scale digital computer, named ENIAC, an acronym for Electronic Numerical Integrator and Computer, calculated trajectories of artillery shells and parameters for the first hydrogen bomb before attacking the problem of climate modeling. In 1950, ENIAC achieved real-time climate predictions whereby 1 minute of calculations estimated air movements for the next minute. As digital computers became more sophisticated, so did the GCMs. GCMs have expanded to take full advantage of the advances in computer science, and their insatiable appetite has been a major driving force spurring the development of even faster and larger machines. Contemporary GCMs continue to balance the finite nature of computer resources against the need for simulating climate over long periods and at high spatial and temporal resolutions. Potentates from King Philip II of Macedon to the present day have espoused the philosophy of divide and conquer as a solution to the world's problems. In computer science, a divide and conquer algorithm is one that splits a problem into ever greater number of related subproblems until the solution to each becomes relatively simple. GCMs follow this philosophy in several respects. First, GCMs divide the planet into a minimum of 2 compartments, atmosphere and oceans. Many GCMs also treat sea ice and land separately. Each compartment has its own model that characterizes processes intrinsic to the compartment and transfers of material and energy with other compartments. These models are in themselves large computer programs consisting of over 100,000 lines of code that undergo independent development. Integrating all the pieces into a coherent semblance of Earth requires another large computer program called a coupler that coordinates both the timing and format of data exchange among the atmosphere, ocean, sea ice, and land models. Second, each compartment model is further divided into submodels. In particular, an atmosphere model usually has discrete subunits for both A. Fluid dynamics, B. Precipitation and clouds, C. Atmospheric chemistry, D. Aerosols, and E. Parameterization of physical processes such as radiation and convection. An ocean model has submodels for A. Wind stress of surface mixing layers, B. Interior ocean fluid motions, and sometimes C. Freshwater inputs such as river runoff. A land model may have submodels for carbon cycling, vegetation, and albedo. Each submodel may again be divided into sub-submodels, and so on until all the processes which are being simulated become sufficiently diminished in complexity to be tractable. Third, GCMs divide the world into a patchwork of grid boxes operating over a relatively short period of time. There are several types of grid systems and time steps, and sometimes a single GCM will use a different one for each submodel. Generally, the smaller the size of a grid box, the shorter the time of a time step. No matter what grid system or time step a GCM uses, the laws of physics, conservation of momentum, conservation of mass, conservation of energy, apply to every grid box during every time step.